welcome back. This is lecture 33. So we were discussing differential amplifier and its various avatars, right, in the last few lectures. So a very 1000 feet overview of what we were discussing till now was the following. So we wanted to make a voltage controlled voltage source of gain of more than 1, right? And for that we said that we will use negative feedback, we'll resort to negative feedback, and we'll compare the desired output with an actual output, right? And we came up with this architecture where this guy had to be again A which tended to infinity. If this was the case, right, if this were the case, then V0 will be equal to K times Vi. And we also saw that this contraption is likely to have a very low output impedance, right, which means that this would have this would act like a voltage controlled voltage source. And then we said that, okay, so how do I realize this gain of A? So only gain block that we knew was a common source amplifier, and so we replace this with a common source amplifier, right? A common source amplifier with some RD, right? Instead of RD, we can call this an R out, right? And this voltage control current source was supposed to be GM times VE, correct? Where VE is the error voltage, and this is how we were supposed to connect it. But then we saw there was a problem with this connection. What was the problem? The problem was that this becomes a positive feedback loop because there is an inversion in the common source amplifier, right? So here we can break the loop anywhere. Let's break the loop here and insert a increment. If that voltage increases, then this voltage decreases. If this voltage decreases, this voltage decreases. So once it goes to the summer, there is one more sign inversion, which means this voltage increases, which means this becomes a positive feedback loop. So what we said that given that we have to use a common source amplifier because that was the only gain block that we knew, what was the other fix? The other fix was to invert the signs of the loop itself, right? So we can say that this becomes the sign of the loop, right? So in this case, we go around the loop the same way. So this voltage, let's say it increases because of some injection, this voltage increases. So this decreases, so this decreases. As you can see, if I inject any disturbance in the loop, right, externally, then the loop has an action of reducing the disturbance, right? So this is negative feedback. So the signs of the signs are all right. Okay. So if the signs are all right, this is fine. So now how do we, and then we said that, okay, fine, if this is okay, how do we actually club this? How do we arrange this summer, and how do we make the entire arrangement? Then we said that, okay, this seems like GM times VE is equal to what? GM, if this is VF. So GM times VE is essentially GM times VF minus VI, right? VF minus VI, because VE is equal to VF minus VI. Okay, so that was all good. Then we said that, okay, then how do I use this summer? Then we knew that a common source amplifier, this voltage source, right, this control current source responds to the difference between the gate and the source voltages. So we were trying to see if we can get rid of all these things and directly apply the feedback voltage here, and if we can make this voltage equal to Vi, then we are good, right? But then we saw that if Vi has a resistance, and which then this is a low impedance node, the source terminal is a low impedance node. If the source terminal is a low impedance node, then the feedback voltage from here, it has an infinite impedance, but this impedance is 1 over GM, right? So which means this is not particularly a this can load the whatever is driving that node. So then we said that this probably is not a very great idea. So what we can do is maybe use a voltage buffer, and apply a voltage Vi, right? So then we rearrange this circuit in a slightly better way, right? So that it made sense. So what did we do to rearrange? We said that so let's do this instead of so let's do this. So ultimately this is a voltage control current source. So this is Vf, right? This is R out. So this is Gm times Vf minus Vi, and this becomes Vi, right? So how do I realize this buffer? This buffer we could realize using a common drain amplifier, right? This buffer could have been realized using a common drain amplifier, and a common drain amplifier was nothing but this, where we apply an input Vi, right? And this becomes a source node, a common source node, correct? This has to be connected, okay? So then we this eventually became the small signal equivalent of our differential amplifier, and over the course of last few lectures we have been trying to figure out the properties of this guy, right? We have been trying to figure out the properties of the stuff inside the sky blue box, right? Since we are trying to figure out the properties of the sky blue blocks, we didn't consider the feedback network at all, right? So now if we go back and try to consider the feedback network, what will it look like? So essentially the stuff inside the sky blue box was a differential amplifier, and we saw multiple versions of the differential amplifier. The last version that we saw was a differential amplifier with a current mirror load, and let's sketch that first. Okay, this was Vi, and this is supposed to be Vf. We have been calling these V1 and V2, right, over the course of last few lectures. But if we have to equate this picture with this picture, then it seems like this node will be Vf and this node will be Vi incrementally. But if we have to use if we have to add bias, then this should be plus some VCM. This should be plus some VCM, right? And so what will be the output voltage? This will be the output. And if I have to equate this picture with our total picture, what will I end up with? We'll end up with this structure where, so let me use some different color code. So this guy is this. So this is K minus 1 R, this is R, right? So Vf is V naught over K, and the feedback loop is closed. Okay, fine. So do you see the relation? Do you see the similarity between this structure and this structure? So the structure that we have in this page is essentially a very rudimentary small signal equivalent of this structure. But now we know the differential amplifier. A differential amplifier has an equivalent GM and equivalent output impedance, and we can then replace this differential amplifier with its overall small signal model, and that would have been what? So differential amplifier in our case, a very rudimentary or a very block level way of representing a differential amplifier was this, right? So this is plus, this is minus, and this is some equivalent GM, and it has some equivalent R out. Okay, so if the structure on the left and the structure on the right have to be same, which one do you think is VI? Which of these two input terminals is VI and which terminal is VF? How will you go about analyzing that? So we can go about analyzing the same using the same way that we have been doing earlier. So let's say we break the loop here and we increase the voltage there, right? If we increase the voltage there, what's going to happen? What's going to happen to V0? So what's going to happen to the incremental current? If we increase the voltage there, this incremental current, right, this I will increase, which means I am effectively drawing current out of V0, right? So which means V0 will decrease. If V0 decreases, right, if V0 decreases, then this guy decreases. So this is a negative feedback. That is well and good. But what is the relationship between the terminal VF and V0? If VF increases, V0 decreases, which means there is an inverted relationship between VF and V0, right? So in the structure, in the symbol in the right, which one should be VF? So clearly this terminal should be VF and the other terminal should be VI, correct? So now if we have to equate the structure on the right and the left, what should I do? I should basically complete the loop by connecting the feedback around it, and this becomes R, this is K minus 1. Okay, fine. So in case of a differential amplifier, right, in case of our differential amplifier, this is by the way small signal equivalent. Right, this is a small signal equivalent, doesn't show any bias. Okay, so in case of a differential amplifier, what is GM? GM is GM of M1 or M2. They are essentially the same. If they are not same, then we can say that this is equal to GM1 GM2 by GM1 plus GM2. And what is R out? R out was RDS2 parallel RDS4, right? So this is obviously the second is obviously under the condition that M1 is equal to M2 and M3 equal to M4. Otherwise RDS2, I mean, there were a lot of current mirroring and all those things used to happen. If those conditions wouldn't have been fulfilled, then we probably will get a different expression, right? So for now, let's assume that everything is identical, that is M1 is equal to M2. So this is under the condition is M1 is equal to M2, M3 equal to M4. Okay, fine. But there is one more rudimentary thing that we didn't talk about. The stuff that we didn't talk about is if your feedback is just like when you said that feedback, the gain of the amplifier has to be infinite. If the gain of the amplifier, it cannot ever be infinite, it has to be very large. If it is large enough, then what do you think V0 will be and what do you think VF will be? Incrementally V0 will be K times VF. V0 will be K times VF, and VF will be equal to VI because of what? Because ultimately we saw that if the loop gain is infinity, the inputs of the error amplifier have to track each other, right? Because that was the only solution. So which means this is equal to K times Vi. Okay, so V naught has to be equal to K times Vi. Now the way I have sketched the circuit on the left, right, there is no distinction between the incremental and the small signal equivalent. And what is the implication of that? The implication is the following: under DC condition, right? Under DC condition, let's say we haven't applied any input, right? We haven't applied any input. It's a VCM. So we haven't applied any input. If we apply VCM to M1, right? If we apply VCM to M1, right? So if we apply VCM to M1, what's going to happen? What's going to happen to VF? VF will also be approximately equal to VF will approximately equal to VCM because of negative feedback, large loop gain, and so on and so forth. If this is equal to VCM, what is this current? This current is VCM over R. Note that we are doing quiescent, right? If this is VCM over R, what is this voltage? This voltage becomes K times VCM, right? So if let's say VCM is, I don't know, 1 volt and K is 5, then V naught becomes quiescent twice 5 volt, right? So now if you're operating with a VDD of, let's say, 5 volt or less, then obviously this is not possible because you cannot have any quiescent voltage larger than VDD. So what's the solution? Let's say we want a gain of K, but we don't want a gain of K on quiescent, right? So what should you do? So the obvious thing to do is to recognize the fact that this node need to be small signal ground, right? That need not be a absolute ground, right? So which means that what we can do is, given that we know that this voltage at VF will become VCM because of negative feedback, so what we can simply do is add a battery of value VCM here. If we add a battery of value VCM here, under quiescent condition, what will be this current? This current will be almost equal to 0 because VF is equal to VCM, which means what will be V naught under quiescent? V naught will also be VCM, right? So that way the problem of setting up the bias is solved, and however incrementally this node is still grounded, so we are still getting an incremental gain of K, correct? But now you might say that we cannot use multiple power supply, multiple sources. You are correct, but what is the solution? The solution is same old, what we have been doing forever. We can add a capacitor, a large capacitor, and call it C infinity, right? If this is the case, right? So what will happen to this node? This node will become open, right? This node will become open under DC condition, which means no current will flow through this stack. If no current flows through this stack, this will be VCM. The loop will set this voltage to VCM. V naught will be equal to VCM, but V naught will be equal to VCM in the absence of input. In the presence of input, let's say I have an input plus Vi, V naught will be VCM plus K times Vi. So this way we can essentially solve the problem of the biasing voltage going out of range. Okay, fine. So let's stick to this architecture for a bit more time. So incrementally, if this is Vi, this is Vf, incrementally this is round, this is V naught, this is Gm, right? And we have to drive some output impedance. Let's say we have to drive some external load, because ultimately we make a amplifier to drive some load. So we need to figure out whether the amplifier has a capability to drive this load. By capability, I mean, what do I mean? I essentially mean that whether whether if in the absence of the load, I will have some voltage, right? When I connect the load back, will I have the same voltage, or the voltage will drop appreciably? So what is the test? The test is to find out the output resistance, right? Or the Thevenin output resistance. So let's find out the Thevenin output resistance of this structure. What will be R out? So in order to figure out R out, what should we do? We apply a test voltage here, right? And find out what is I test. So if I apply a test voltage here, what is the voltage at Vf? This is K minus 1 R. This is R. So what is the voltage at Vf? That is V test over K, right? So by the way, we have to short input because we are trying to find out impedance, right? We have to desensitize all independent voltage sources. So this is V test over K. So what is the current that is coming out of the GM? This is a voltage control current source. In this case, the V test over K voltage is appearing at the negative terminal, which means the negative current will come out, or in other words, the positive current will get sucked in, right? So the current that will get sucked in, is GM times V test over K, right? Okay. So what is the total current? What is I test? I test equals GM times V test over K plus the current that is flowing through this node, this stack, which is V test over KR plus the current that is flowing through the output resistance, which is V test over R out. Okay, so what is I test over V test? That is GM over K plus 1 over KR plus 1 over R out, right? So as long as you can ensure, so if GM over K is much greater than 1 over KR plus 1 over R out, right? Or in other words, I can say that K over GM is much less than the parallel combination of R out and KR, right? So as long as we can ensure that, right? So this, our output impedance, effective output impedance. So let's sketch this circuit again. I probably have to use a different terminology instead of R out, because we can use R out of the GM, right? So this is ROGM, because R out of the entire block should be called R out, ROGM. So what is the output impedance of this? R out becomes almost equal to K over GM, and as long as this is much less than RL, if this is true, right? Or that is, as long as GM times RL. So what is RL? RL is resistance that I am planning to drive. As long as GMRL is much greater than the intended gain K, right? The structure behaves like a VCVS of gain K, right? Okay. So So this is something that is a very good thing, because what is K? K is a ratio of resistances, and K is, note that K is independent of process voltage temperature variations. Okay, so if you recall the characteristics of a good voltage control voltage source that we desired was, we should have gain of at least more than 1, that's for sure. We should have the gain which is independent of RL, and we should have a gain which is independent of PVT, right? So a simple common source amplifier was able to give us a gain of more than 1, okay, but it was not able to give us a gain which is independent of PVT, and it was also not able to give us a gain which was independent of RL. Now if we consider and we say that, okay, if the intrinsic, if the GDS or if the RDS of our common source amplifier, the output impedance of the common source amplifier was much lower than RL, then sure we get a gain which is independent of RL. Yes, indeed we get. However, still the third point is not valid. That is, the gain is still dependent on process voltage temperature, right? However, when you make a when you make an amplifier using the principles of negative feedback, it is possible to meet all three criterions. That is, you make a amplifier of gain K, where K has to be, I mean, obviously K has to be greater than or equal to 1, else it doesn't make a difference. So as long as K is more than or equal to 1, you can use the principles of negative feedback to get a amplifier of gain more than 1, right? Now, however, you see that there are certain issues, right? So what are the issues? The issue that this structure has is, we saw that the what was the output range, output common mode range? What was the range at what was the range that the output can swing till all the transistors are in saturation? For example, if I take this guy V0, what is the maximum it can swing to? The maximum it can swing to is what? VDD minus 1 overdrive voltage of M4. So that is good. It can swing quite high towards the supply voltage, right? But what is the lower side problem? How low can V0 go? V0 only can go VCM minus 1 threshold voltage, right? Since V0 can go only VCM minus 1 threshold voltage, then which means that we can potentially have a problem, because you are not allowing the output to swing too much, right? So that is one problem. What is another problem? Another potential problem is, if RL is very low, right? So which means that, let's say we are not able to meet this criteria. We are not able to meet these criteria. GMRL is much greater than K. Then RL will end up loading our differential amplifier, right? If our differential amplifier gets loaded, then we'll not be able to impose the same condition that the gain is very high, right? What is the gain? What in that condition of A, what is the gain? The gain is that gain, right? So if I have to equate this structure with, this structure with this structure, what is the gain if I have to equate these two structures? So even without getting into too much detail, what we need to do to figure out the gain, we can simply disconnect the feedback. We can simply disconnect the feedback and find out the gain between Vi and V0, right? So if I disconnect the feedback, here, and let's say incrementally ground it, what will be the gain between Vi and V0? And if I apply Vi here, the gain will be GM times all the resistances in parallel, correct? So if that gain, if the gain becomes gm times all the resistance in parallel, if that gain goes to much closer to 1, right? If a has to be ideally infinite, that gain has to be much closer to infinity, or rather it has to be high, right? So if that gain becomes lower, what is lower? Lower is the gain has to be with respect to 1, right? You remember it was like loop gain by 1 plus loop gain. So if the gain becomes comparable to 1, then all the good things of negative feedback go for a toss. Your negative feedback will no longer be valid, which means your output will not be k times vi, which means you are going to have more and more steady state error, so on and so forth, right? So hence you have to ensure that the open loop gain, right, after you break the loop, you will find an open loop gain. That open loop gain has to be much more than 1, right? So if the open loop gain is less than 1, then we are in a trouble, right?